The objective of this lecture is to provide two examples demonstrating the application of Newton's second law to problems in particle kinetics. The two examples that will be studied in this lecture are a particle moving while in contact with a one-dimensional curve and a particle moving while in contact with a two-dimensional surface. These two types of problems have the following characteristics. So, a particle moving while in contact with a one-dimensional curve So the characteristic, or the key characteristics of this type of problem are as follows. First, the system of this kind has 1 degree of freedom. This is a 1 degree of freedom problem, which implies that there's going to be one differential equation. Now, the key aspect of determining this differential equation is as follows, is that the unknown reaction force lies in a plane spanned by the principal unit normal and the principal unit binormal to the curve. As a result, the differential equation is obtained by taking the component of Newton's second law in the direction normal to this plane, which is the direction, I should say, which is the same as taking the component of Newton's second law in the direction tangent to the curve. Now, in the second case, where we have a particle moving while in contact with a two-dimensional surface, in this case, the situation is a little bit different. This one is a 2 degree of freedom system, which implies that there are two, or I should say a system, of 2 differential equations. In this case, the unknown normal force, remember it's the same thing, unknown normal force, which is the reaction force, lies in a direction orthogonal to the plane, to the tangent plane of the surface at the point of contact. Thus, the tangent plane can be spanned by two orthogonal directions and the system of differential equations, in this case two differential equations, are obtained by taking components of Newton's second law along these two directions that span this tangent plane. So in this lecture, for the remainder of this lecture, we're going to study two examples that are going to allow us to be able to see the difference between a particle sliding on a curve and a particle sliding on a surface, or moving while in contact with a curve and moving while in contact with a surface. These two examples are going to be studied in quite a bit of detail, and as we move through the examples, we'll be able to see the key features of each type of problem. So the first type of problem is as follows. A particle sliding while in contact with a curve. So here's the example. We have a particle that slides or moves on a parabola. The parabola is a track, and this track rotates about the vertical with angular velocity omega. The particle has mass m. The projection of the particle into the horizontal plane is a point called Q. The base of the parabola is labeled O, and the displacement of the horizontal displacement is denoted by a variable called x, and that's the displacement from O to Q. And the equation for the parabola is y equals x squared over 2b. We have the following forces that are acting on the particle. Gravity acts downward, and there's a friction force, which is a viscous friction force with a viscous friction coefficient, C. And the objective is to determine the differential equation of motion for the particle in terms of the horizontal displacement x. Now, in order to solve this problem, we have to apply Newton's second law. So we're going to apply Newton's second law. Now, Newton's second law is stated as the force is equal to the mass of the particle times the acceleration of the particle in a frame I'm going to call I. I is equal to an inertial reference frame. Now, as with all problems, we have to approximate an inertial reference frame. So in this example, or in this problem, an inertial reference frame will be taken to be, which means approximated, as the reference frame relative to which the track, which is the parabola, rotates. Now, just for clarity, we'll call this the track, which I'll label T. Okay. So in this problem, there's one rotation. So we have to do both kinetics and kinematics now because we're applying Newton's second law. So we're going to do the kinematics first. The kinematics, the goal is going to be to determine the inertial acceleration. So we have to get the acceleration of point P as viewed by an observer in an inertial frame. I'm going to do the kinematics somewhat backwards in the sense that I'm going to do the coordinates fixed in the rotating frame first, and then the coordinates fixed in the inertial frame. So I'm going to let T equal the track, and then the coordinates that are going to be fixed to the track are going to have the origin at O. I'm going to put little ex along OQ. I'm going to say that EY is along omega, and that EZ is equal to EX crossed with EY. Then the inertial frame, which is my base frame, is going to have its origin also at O. And then I'm going to say that EX, EY, EZ is going to equal little ex, little ey, little ez when t equals 0. So that gives me the coordinates fixed in the inertial frame. Now, the position of point P relative to O, because O is fixed in the inertial frame, so that's where I have to measure all my distances, is going to equal x ex plus y ey, which is going to equal x ex plus x squared over 2b times ey. So now I have to compute the inertial acceleration. So I first have to compute the inertial velocity and then take its rate of change to get the inertial acceleration. So the velocity of point P as viewed by an observer in the inertial frame is equal to the rate of change in the inertial frame of the position of P relative to O, which is equal to the rate of change in the track of the position of P relative to O plus the angular velocity of the track in the inertial frame crossed with the position of P relative to O. So the first rate of change that I need to compute is the rate of change of the position of P relative to O in the track, and that's equal to x dot ex plus xx dot over b ey. And for later, I'm going to need this. So I'm going to call this the velocity of point P as viewed by an observer fixed in the track. So it's in the track. So now, I have this velocity as viewed by an observer fixed in the track. I have to then add to that the angular velocity of the track in the inertial frame crossed with the position of p relative to O. The angular velocity of the track is equal to omega Ey, and then this is, take the vector product with xex plus x squared over 2b Ey, which is equal to minus omega x Ez. So therefore, the inertial velocity is equal to x dot Ex plus x dot over b y minus omega x Ez. And one other thing that I didn't state at the beginning here, let's just make this clear. B is a constant, and we're also going to assume that the magnitude of omega, which is equal to omega, is also equal to a constant. So that way we don't have to deal with rates of change of omega. So that's the inertial velocity. So then the inertial acceleration is equal to the rate of change in the inertial frame of the inertial velocity of the particle, which is equal to the rate of change in the track of the inertial velocity plus the angular velocity of the track in the inertial frame crossed with the inertial velocity. So the rate of change in the track of the inertial velocity is equal to x double dot Ex plus x dot squared plus x double dot over b Ey minus omega x dot Ez, because I assumed that omega was constant. The angular velocity of the track in the inertial frame crossed with the inertial velocity of the particle is equal to omega Ey crossed with x dot Ex plus x dot over b Ey minus omega x Ez, which is equal to minus omega x dot Ez, and then Ey crossed with Ey is 0, and Ey crossed with Ez is Ex, so I get minus omega squared x Ex. So therefore, the inertial acceleration of the particle is equal to x double dot minus omega squared x times Ex plus x dot squared plus x double dot, all divided by b times Ey minus 2 omega x dot Ez. Now you'll see that when I computed this acceleration, I used Cartesian coordinates that were fixed to the track because the particle is naturally, the motion, or I should say the position of the particle is naturally parametrized in terms of Cartesian coordinates that are fixed to the track, which is why we wind up with an expression in terms of 3 Cartesian directions based on the fact that we started with a position that was expressed in Cartesian coordinates. So that's the acceleration, and that's the end of the kinematics portion of the problem as far as computing purely kinematic quantities. But we're going to need kinematics again when we actually get to kinetics, because you'll see that there are going to be pieces of the kinetics that are going to require us to also do kinematics. So let's do the kinetics. So the kinetics of this problem are a little more involved than what might actually seem at first glance, but let's do it. So here's the particle. I have the force of gravity that acts downward. I have a friction force, and then I have a normal force. Now, what's important about some of this is that I don't know the direction of the normal force. The friction force and the force of gravity, I'm going to be able to compute them because this is viscous friction, so I'll be able to figure them out. But the normal force, I don't know it exactly. So let's write down these forces, and then we'll figure out what directions they lie. So mg is equal to the force of gravity. F sub f is the friction force. And then N is the normal, also called the reaction force. Now, what directions do these forces lie? Well, the first one is the force of gravity. It lies in the direction, in the minus EY direction. The next one is the friction force. Now you recall that this is viscous friction. So viscous friction has the model that it's minus the coefficient of viscous friction times the velocity as viewed by an observer fixed to the curve. Now the important thing about this is not the inertial velocity that's used to compute the friction force. It's the velocity as viewed by an observer fixed to the curve. The curve in this case is the track. Now, given the fact that it's equal to minus c times the velocity as viewed by an observer fixed to the track, I can also write that as minus c times the speed relative to the track times the tangent vector, where et is the tangent vector to the track. It's not the tangent vector to the inertial frame, but it's the tangent vector to the track. That's really important, that that vector, et, not be confused with the velocity in the inertial frame. It's actually along the direction of the velocity relative to the track. Now the last force that we need to compute is we need to figure out this normal force. But we're dealing with a particle sliding on a curve. And the curve is a one-dimensional object in 3 dimensions, so the normal force has 2 components. It's in the plane spanned by En and Eb. And if you remember, when we go all the way back to my description at the beginning of this lecture, I said that in the case of a particle sliding on a curve, the unknown reaction or unknown normal force lies in the plane spanned by the principal unit normal and the principal unit binormal to the curve. And the curve in this case is the track. So as a result of that, this is the expression for the unknown reaction force or normal force. So now we can see that there are 2 components to this reaction force, and I'll just put a reminder here that Et, En, Eb is an intrinsic basis relative to the track, which, as a reminder, is the parabola. Now, given the fact that we're dealing with motion relative to a track, and this is the intrinsic basis, we can now see that the sum of the forces, because we're going to apply Newton's second law, we're going to apply F is equal to ma p I. And as a result of this, we're going to actually get the following result. So F is equal to mg plus n plus F sub f, or let's write it in the same order that we developed the forces. Now, because, this is really important, because n lies in the En Eb plane relative to the track, there is no component of n in the Et direction. So that implies that n dotted with Et is equal to 0. So that's really important, because then we can get the differential equation. So the differential equation can be obtained, or is obtained, by taking the component of Newton's second law in the direction of ET. In other words, we're taking the ET component. So, now, if we do that, what exactly do we get? That means that F dotted with ET is equal to MAPI dotted with ET. And why do we get that? Well, we just said that N dotted with ET is equal to 0. So what is F dotted with ET? Well, F dotted with ET is going to equal mg plus F sub F plus N dotted with ET. But that's equal to mg dotted with ET plus F sub F dotted with ET, and that's because N dotted with ET is equal to 0. So, now let's figure out how to do the rest of this. Okay, so now we now know that this is the differential equation that I've got there highlighted. F dotted with ET equals the mass times the inertial acceleration dotted with ET. So now let's go through the process of computing this. So first thing I need to do is I need to compute ET. So I know that ET is equal to the velocity of P as viewed by an observer fixed to the track divided by the speed. But you'll remember that at the beginning of the problem, I actually computed the velocity as viewed by an observer fixed to the track. I actually used it on this page right here, and I can actually use that now to be able to compute this tangent vector. So recall that the velocity of point P as viewed by an observer fixed to the track is equal to x dot EX plus x dot over b EY. So that gives me that I can rewrite this velocity relative to the track as x dot times EX plus x over b EY. And from that, I can now compute the speed. So the speed is equal to x dot times the magnitude of the vector that's in the parentheses, which is 1 plus x squared over b squared to the 1/2. From this, I can actually now compute the tangent vector. So the tangent vector becomes x dot times EX plus x over b EY, all divided by x dot times 1 plus x squared over b squared to the 1/2, which is equal to, I get EX plus x over b EY, all divided by 1 plus x squared over b squared to the 1/2, which is equal to BEX plus x EY, all divided by x squared plus b squared to the 1/2, where what I did was I multiplied the numerator and denominator through by b. So there is my tangent vector relative to the track. Now I have the tangent vector relative to the track. So now we can compute both sides. So let's compute both F dot ET and MAPI dotted with ET. What do we get when we do that? Well, F dotted with ET is equal to minus mg EY minus c times the speed relative to the track times the tangent vector dotted with the tangent vector, which is equal to minus mg EY dotted with ET minus c times the speed relative to the track, because the tangent vector dotted with itself is 1. So if I substitute, I get minus mg, and then I've got EY, and now I have to take the dot product with the tangent vector, but the tangent vector is equal to b ex plus x ey, all divided by x squared plus b squared to the 1/2 minus c times the speed relative to the tangent vector, which is equal to minus mgx, all divided by the square root of x squared plus b squared minus c times the speed. Well, the speed was equal to x dot times 1 plus x squared over b squared to the 1/2, which we can rewrite as minus mgx all divided by x squared plus b squared to the 1/2 minus c. And now I'm going to do the same thing. I'm going to factor out the b, so x dot over b times x squared plus b squared to the 1/2. So this is f dotted with et. Now we need to compute ma dotted with et. We need mapi dotted with et. So what's that? Well, let's figure that out. The mass times the acceleration is the mass times x double dot minus omega squared x times ex plus x dot squared plus x double dot all divided by b ey minus 2 omega x dot ez. This is going to be dotted with this tangent vector, which is equal to bex plus xey all divided by x squared plus b squared to the 1/2. So what's that equal to? Well, that's equal to m times. Well, let's take the dot products. We've got ex components and ey components. The ez component doesn't show up. So we get x double dot, we get b times x double dot minus omega squared x, all divided by x squared plus b squared to the 1/2. That's the ex dotted with ex term, and then there's an ey dotted with ey term. And then I get plus, I've got x times x dot squared plus x double dot, all divided by b times x squared plus b squared to the 1/2, which I can rearrange a little bit if it makes it a little bit easier to follow the expression. But the denominator has an x squared plus b squared to the 1/2, and the numerator is going to have if I actually put this over, I can put a b in the denominator of the whole thing. And so what I wind up with is b squared times x double dot minus omega squared x plus x times x dot squared plus x double dot. So all I did there was I multiplied the first term, numerator and denominator, by b, and then I just combined them. So that, remember, this is equal to the mass times the inertial acceleration dotted with et. So now I have a way of being able to equate these two sides. So here's the force dotted with et. So because F dotted with et equals MAPI dotted with et produces the differential equation. We have the following. So what do we have? Well, we've got minus mgx minus mgx all divided by x squared plus b squared to the 1/2. That's this term. And then we have minus c x dot over b, and that's times x squared plus b squared to the 1/2. And that has to equal the other side. Well, the other side is equal to m times, we've got b times x squared plus b squared to the 1/2. And in the numerator, we've got b squared times x double dot minus omega squared x, and then plus x times x dot squared plus x double dot. And that is the differential equation of motion. Now, it doesn't look very elegant because it's a pretty complicated differential equation, and it can be simplified a little bit to be able to get it into a slightly better sort of condition from what it is right now. But that last result, rearranged, is actually the differential equation. And I'll make one rearrangement to it, which will actually simplify it a little bit. Suppose we multiply the whole thing through by x squared plus b squared to the 1/2. So multiply through by x squared plus b squared to the 1/2. And then what we get is we get minus mgx minus cx dot over b times x squared plus b squared, because we're multiplying the square root by itself, so we get x squared plus b squared. And that is going to equal, so now in the denominator, things start to drop out. We get m times, and if we just remove the b now, we get m times b times x double dot minus omega squared x, and then plus x over b times x dot squared plus x double dot. And that is the differential equation of motion. So that last result, and you can rearrange it further if you want to. You can combine the x double dot terms, you can combine the x dot terms and the x dot squared terms, and you can get it into a different form. But that is the differential equation of motion. And what's really important, this is the key concept. So the key concept is that the differential equation of motion was obtained by taking the component of Newton's second law in the direction of the tangent vector to the track, because the unknown reaction force, or the unknown normal force, is in a plane, is in a plane spanned by the principal unit normal and principal unit binormal to the track, right? And because that normal force was in the plane spanned by the principal unit normal and the principal unit binormal, when you take the scalar product in the direction of the tangent, so we can write it this way, as a result, n has no component in the tangent direction to the track, which produces, say it this way, thus allowing the differential equation when taking the scalar product of F equals MAI in the direction of ET, where ET is the tangent vector to the track. So that finishes this example, and we're going to do one more example now. And the next example we're going to do is we're going to do an example of a particle sliding on or moving while in contact with a two-dimensional surface. The second example that's going to be studied in this lecture is the following problem. A particle slides on the inside surface of a cone. So I'm going to draw the cone first. So let's draw the cone. The cone is given as follows, and there's a particle that's located on the inside surface of this cone. The cone is defined by a half angle. That half angle is defined as beta. And to make it a little easier to visualize how this is all set up, I'm going to start by laying down a set of axes that are actually fixed to the cone. I'm going to call these directions EX, EY, and EZ. And the cone's position, the particle's position on the cone is going to be defined in terms of a set of cylindrical coordinates where the angle measured from EX is theta, and the distance from the apex of the cone at O to the projection of the point P into the horizontal plane, which is the EX-EY plane, is going to be called Q. Now, to make this problem a little bit simpler, we're going to include gravity, but in this particular case, I'm just going to assume there's no friction. We can add friction later if we want to. Maybe you'll study it a little bit later, but right now I'm just going to assume no friction. So let's just say that right at the beginning, no friction. Now, the goal of the problem is the same as the goal of the problem was in the previous example, except for now we have a particle sliding on a surface. As a result of that, we're going to have to determine two differential equations of motion. So let's write this down. So the objective is going to be to determine a system of two differential equations for the particle in terms of the variables r and theta. So I need two differential equations. It's going to be a system, so they're going to be coupled differential equations, and we're going to determine them using the fact that since the particle slides on a two-dimensional surface, the reaction force is normal to the tangent plane at the point of contact, and thus there are going to be two directions that are going to lie in that tangent plane that I can use to take the components of Newton's second law along those two directions and determine the differential equations. And we'll actually see how this works when we actually go through the problem. But in the beginning, we're going to do the same thing that we did before, which is that we need to apply Newton's second law. Now, in this particular case, I'm going to use the surface as the inertial reference frame. So the cone, which is going to be defined as S, will be taken as the inertial reference frame. Now, you could also call this the ground, but I want to make sure that it becomes clear that we're dealing with a surface and that the surface is inertially fixed. So we're going to call it S. So all of our rates of change are going to be computed relative to S. Now, when you look back at the picture, so here's the picture again, you see that I'm going to describe the position of this particle in terms of cylindrical coordinates, and as a result of that, I'm going to have two reference frames again because I have a rotation which is going to be defined by a plane. So let's write down the two frames. So S is equal to the inertial reference frame, and that's the same thing as the cone. And I've already actually set up the coordinate system fixed in the inertial frame. The origin's at O. EX is along, or I should just say EX as given. And then EY is also as given. And then EZ is the same as given, as I gave you that coordinate system. The next thing is going to be, I'm going to call this frame A. And A is going to equal the plane. Now let's look back here. It's going to be the plane defined by EZ and OQ. So it's the EZ OQ plane. And that is going to have, the coordinate system is going to have, again, its origin at O. Now I'm going to put ER along OQ. Little ez is going to be the same as big EZ. And then E sub theta is equal to EZ crossed with ER. Now, once we do that, we can actually describe the position of P relative to O in terms of cylindrical coordinates. So in order to do that, I need to figure out what the equation is for the cone. So here's Z. So if I look at a cross-section of the cone, let's look at this cross-section. Here's the cross-section where the particle is. So imagine the particle's resting on, or not resting, but it's in contact at that point. You can see that this distance is Z, and this is R. So this is R, and this is Z. And this angle here is my cone half angle, and that's beta. So if you actually look at the equation, you'll actually see that if I drop the horizontal over here, you can see that the tangent of beta is equal to R over Z. So the tangent of beta is equal to R, which is the opposite side, over the adjacent side, which says that the cotangent of beta is equal to Z over R, which gives that Z is equal to R times the cotangent of beta. So that gives me the equation for the cone. So then, what I can do is, I can write the position of P relative to O is equal to RER. Well, actually, let's do it in two steps. It's the position of Q relative to O plus the position of P relative to Q, which is equal to RER plus ZEZ, which is equal to RER plus R times the cotangent of beta times EZ. So there's the equation that defines the position of P relative to the apex of the cone. Now, I need the inertial velocity and the inertial acceleration. So the inertial velocity is the velocity of P as viewed by an observer fixed to the surface, because the surface is my inertial frame. So this is equal to the rate of change in S of the position of P relative to O, which is equal to the rate of change in A of the position of P relative to O, plus the angular velocity of A and S crossed with the position of P relative to O. Now that is equal to, I've got R dot ER plus R dot cotangent beta EZ, and then the angular velocity of A and S is theta dot EZ, crossed with RER plus R cotangent beta EZ, which is equal to, I get R dot ER plus R dot cotangent beta times EZ, and then I get plus R theta dot E theta, which leaves that the velocity of P as viewed by an observer fixed to the surface is equal to R dot ER plus R theta dot E theta plus R dot cotangent beta times EZ. Now, we need the inertial acceleration, right? Because we're going to apply Newton's second law, and we're going to apply it using the inertial reference frame being the surface of the cone. So the acceleration of P as viewed by an observer fixed to the surface is equal to the rate of change in S of the velocity of P in S, which is equal to the rate of change in A of the velocity of P in S plus the angular velocity of A and S crossed with the velocity of P in S. So what does that give me? This gives me the rate of change in A is equal to R double dot ER plus R dot theta dot plus R theta double dot times E theta plus R double dot times the cotangent of beta times EZ plus theta dot EZ crossed with R dot ER plus R theta dot E theta plus R dot cotangent beta times EZ, which is equal to, now let's do this, R double dot ER plus R dot theta dot plus R theta double dot times E sub theta plus R double dot times the cotangent of beta EZ, and then I get plus, now let's see, EZ crossed with ER is E theta, so I get plus R dot theta dot E theta, and then EZ crossed with E theta is minus ER, so I get minus R theta dot squared ER, which gives the acceleration of P as viewed by an observer fixed to the surface is equal to R double dot minus R theta dot squared ER plus 2R dot theta dot plus R theta double dot E theta plus R double dot cotangent of beta times EZ. So this is the inertial acceleration, and this is what we're going to use to apply Newton's second law. Now we need to do the kinetics step. So kinetics is done as follows. First we draw the free body diagram. Of the particle, and here's the particle, and there's a force of gravity acting on this, and there's a normal force. Now the normal force in this case is different from what the normal force was in the case of a curve, or the normal force exerted by a curve. In this case, the force of gravity is the same as the force of gravity was in the previous problem. But the normal force, or the reaction force, in this case, is normal to the tangent plane of the surface. So this is really important, is that N, well, let's do the force of gravity first because it's the easy one. It's equal to minus mg times EZ. But the normal force in this case is equal to N times this little vector n, where n is the unit vector normal to the tangent plane to S at point P. Now, how do we compute that unit normal? Well, we need to use the equation that defines the surface. So recall that z is equal to r times the cotangent of beta. From this, I can actually write the function f of r, theta, and z. Notice that I'm using cylindrical coordinates. I'm going to use r, theta, and z. This is r cotangent beta minus z, and that equals 0. Now, given the fact that this whole thing equals 0, I can now use the following fact, and this is what I started with when we talked about surfaces, is that the unit normal to the surface, which is normal to that tangent plane, is in the direction of the gradient of the surface divided by the magnitude of the gradient. Now, in cylindrical coordinates, the gradient actually looks like this: df dr times er plus 1 over r df d theta times e theta plus df dz times ez. So let's compute that. So what do we get for the gradient? Well, the partial of f with respect to r is equal to cotangent beta, and that's multiplied by er. There's no dependence on theta, and then the last one is minus ez, because the partial derivative of f with respect to z is -1. So there's the gradient. Now, if I want to compute the magnitude of the gradient, it's equal to cotangent squared beta plus 1 to the 1/2, the square root of the sum of the squares, which is equal to cosecant beta. So therefore, the direction normal to the surface in this case is equal to cotangent beta er minus ez, all divided by cosecant of beta. But the cosecant of beta is 1 over the sine, so this is equal to the sine of beta times the cotangent of beta er minus ez, which gives that n is equal to, well, the cotangent is the cosine over the sine, so this gives me cosine of beta er minus the sine of beta times ez. So that is the direction normal to the surface. And now we can then write that n is equal to the component n times that direction. So from this, we now have the force. The force is equal to mg plus n, which is equal to minus mg ez plus n times this direction n. Now, this is where the surface becomes a different situation from what we had with a curve. Is that, let's write this out. Let's see what's going on. Is that it is now necessary to determine two directions that span the tangent plane to S at the point of contact, and take the components of Newton's second law in these two directions that span the tangent plane. Now, what's important here also is that these two directions should be orthogonal to one another. So what I really mean here is that I want two directions that span the tangent plane and are orthogonal. So these two directions that span the tangent plane to S to S at P should be orthogonal to one another. And they're already going to be orthogonal to N because they're in the tangent plane, and N is normal to that tangent plane. So how are we going to get these two directions? So here's how we're going to do it. So N is a unit vector. N is a unit vector. Therefore, we have from the properties of a unit vector that the rate of change of n as viewed by an observer fixed to the surface dotted with n has to equal 0. Now, that comes from the fact that n dotted with n is equal to 1, so when I take the rate of change of n dotted with n, I get 0. And then if I take that rate of change, I get dn dt and s dotted with n plus n dotted with dn dt and s, and that equals 0. There are two of them, so this gives me this result. This result is true for all unit vectors. If I take the rate of change of a unit vector in any reference frame, it's orthogonal to the unit vector itself. So one of the directions that I can get is dn dt and s. So dn dt and s is orthogonal to n. And the third direction, which is the second direction that's going to be in this tangent plane, is going to be the cross product. So let's see what this tells me. Okay, so let's do this slowly. Because dn dt in S is orthogonal to n, the vector dn dt in S lies in the tangent plane to S at point P. And that gives us one direction that's in the tangent plane. The other direction that's going to be in the tangent plane is going to be the cross product of n with this direction of dn dt and s. So let's compute this direction first, and then we'll compute the second vector that's in the tangent plane. So what is dn dt in s? Well, if you go back and look at n, what is n? It's equal to cosine beta er minus sine beta ez. So since it's expressed in the basis fixed in a, this is equal to dn dt in a plus omega as crossed with n. But dn dt in a is 0 because beta is a constant. So this just gives me theta dot ez crossed with cosine beta er minus the sine of beta ez. And this, ez crossed with er, is e theta, so I get theta dot cosine beta times e theta, and the second term is 0. So now I know that this direction, dn dt and s, actually lies in the direction of e theta. So I'm going to say let t1 equal dn dt and s divided by the magnitude of dn dt and s. Well, the magnitude of this vector is theta dot cosine beta, so this whole thing's just equal to e sub theta. So there's my first direction that lies in the tangent plane. Now I'm going to get the second direction that lies in the tangent plane. So if I say that t1 lies in the tangent plane to S at point P, and n is normal to the tangent plane to S at P, then I can construct another direction. If I call like T1 the first direction and I call N the third direction, then if I take 3 cross 1, N crossed with T1 also lies in the tangent plane to S at P. And the reason that N cross T1 lies in the tangent plane to S at P is because T1's in the tangent plane, N is normal to the tangent plane, so the cross product of two vectors is normal to both of the vectors, in which case N cross with T1 is normal to N, and therefore N cross T1 has to lie in the tangent plane. So what we're going to do is we're going to say let T2 equal N crossed with T1. Now N, if we go back, is equal to cosine beta ER minus sine beta EZ. And T1 is E sub theta. So this gives me ER crossed with E theta is EZ, so I get cosine of beta times EZ, and EZ crossed with E theta is minus ER, so I get plus the sine of beta times ER, which, when I flip the order, I get sine of beta ER plus the cosine of beta times EZ. So the two vectors that lie in the tangent plane, T1 and T2, are both orthogonal to N. So what does that mean? That means that I get two differential equations are obtained by taking the components of Newton's second law in the directions of T1 and T2. What do I mean by that? It means that the first differential equation is obtained by F dotted with T1 is equal to mass, the mass times the inertial acceleration dotted with T1, and F dotted with T2 is equal to the mass times the inertial acceleration dotted with T2. Okay, so let's do this now. Let's do this stuff. What is F? Well, F, again, is equal to minus mg EZ plus n times n. So what's F dotted with T1? F dotted with T1 is equal to minus mg EZ plus n times n dotted with E sub theta. Well, we know that n is orthogonal to T1, so therefore n dotted with E theta, or n dotted with T1, is 0, and EZ dotted with E theta is also 0, so this whole thing is equal to 0. What is the mass times the acceleration in the inertial frame dotted with T1? Well, that's equal to m times r double dot minus r theta dot squared times ER plus 2r dot theta dot plus r theta double dot times E sub theta, and then plus r double dot cotangent of beta times EZ. This whole thing is dotted with T1, but T1 is equal to E sub theta. So this gives me m times 2r dot theta dot plus r theta double dot is equal to 0. So therefore, the first differential equation, F dotted with T1, which is equal to the mass times the inertial acceleration dotted with T1, produces the following result. It produces 0, because F dotted with T1 is 0, is equal to M times 2 R dot theta dot plus R theta double dot. This is the first differential equation. How do we get the second differential equation? So if we go back and see the process here, the second differential equation is obtained by taking F dotted with T2 is equal to the mass times the inertial acceleration dotted with T2. Well, what is F dotted with T2? Well, that's equal to minus mg Ez plus n times n, but then dotted with T2. What's T2? T2 is sine beta ER plus cosine beta EZ. Dotted with sine beta ER plus cosine beta EZ. This is equal to, well, I know that n dotted with T2 is 0, so nothing in here is gonna produce anything with regard to n. So I just have to do minus mg Ez dotted with T2, which gives me minus mg cosine of beta, and then Ez dotted with Ez is 1. So that's F dotted with T2. What is the mass times the inertial acceleration dotted with T2? Well, that's equal to the mass times R double dot minus R theta dot squared times ER plus 2 R dot theta dot plus R theta double dot E theta plus R double dot times the cotangent of beta times Ez dotted with this vector, which is the sine of beta times ER plus the cosine of beta times Ez. And what's that equal to? Well, I've got ER and Ez components. So I have M times R double dot minus R theta dot squared times the sine of beta. That's ER dotted with ER. And then I have Ez dotted with Ez plus M times R double dot cotangent of beta times the cosine of beta times Ez dotted with Ez, which is 1. So now, what is cotangent of beta? Cotangent of beta is cosine over sine. So let's simplify this a little bit. What do I have for the force? I've got minus mg times the cosine of beta. So therefore, F dotted with T2 equals MAPS dotted with T2 gives the following result. It gives minus mg cosine beta minus mg cosine of beta is equal to, well, let's look at all this. I've got M times R double dot minus R theta dot squared times the sine of beta, and then I've got plus MR double dot cotangent of beta times the cosine of beta. Now, what I can do here is I can do a little simplification. Cotangent is equal to cosine over sine. So what I can do is I can rearrange this equation. So if I take cosine divided by sine, I get the equation here that I wind up getting is minus mg. Now I'm going to multiply by sine. So I get cosine of beta times the sine of beta is equal to m times r double dot minus r theta dot squared. And then I'm multiplying by sine, so I've got sine squared beta. And then I've got plus m r double dot, and then I've got cosine squared beta. which, when I simplify that, gives m minus mg times the cosine of beta times the sine of beta is equal to, now you'll see here that I have an m r double dot sine squared beta and an m r double dot cosine squared beta, which just gives me m times r double dot, and then I get minus m r theta dot squared times sine squared beta. That's the second differential equation. So this is my second differential equation. So the two differential equations that I have, the first one I already highlighted, and then here's the second one. Now you'll notice that there are two differential equations. So let's note that this problem results in two differential equations, or a system, I should say, of two differential equations. Because a surface removes 1 degree of freedom. It does not remove 2 degrees of freedom, it removes 1 degree of freedom. So when we start, a particle, its position is defined by 3 quantities, so it has 3 degrees of freedom. The surface removes 1 degree of freedom, which leaves 2 degrees of freedom, and those 2 degrees of freedom lead to 2 differential equations. So the end result of this lecture is that we've studied in detail a particle moving on a curve, which has led to a single differential equation that describes the motion of the particle, because a curve takes out 2 degrees of freedom, because it's a one-dimensional object in 3-dimensional Euclidean space. And then we study an example of a particle moving while in contact with a surface, and a surface is a 2-dimensional object, which thus removes 1 degree of freedom, and that 1 degree of freedom leaves 2 degrees of freedom, which gives a system of 2 differential equations. So, going back to the beginning, remember that when a particle slides on a curve, or a one-dimensional curve, the result is going to be 1 differential equation, and it's going to be the component of Newton's second law in the direction tangent to the curve. In the case of a particle moving while in contact with a surface, the 2 differential equations are going to be obtained by computing 2 directions that span the tangent plane of the surface. And those 2 directions in this case should be orthogonal to one another. And then the 2 differential equations are going to be obtained by taking the components of Newton's second law along those 2 directions that span the plane that is tangent to the surface at the point of contact. So hopefully this actually provides a good introduction to how to deal with problems that are where a particle is constrained to either move on a curve or move on a surface. And in future lectures we're going to study more problems of this kind to get more familiarity with how to deal with these types of situations, because they occur quite frequently.